Okay, so hello and welcome back. So we talked about the basically the probability chapter related to class 9. We did a review of that, and that was about I suppose 4 videos, 4 hours we spent on class 9. And we do need to do the same thing for class 10 as well, because these are the basics. If we don't know the basics, then we'll get into trouble when we get to when we'll get to class 11 and class 12. So we need to do the review here. So now let's start with probability class 10. Probability class 10. We will do just a review. We won't go through the exercises, just the concept and some examples, and then we will get to class 11. So to start, as an introduction, it says that in class 9 you have studied about experimental or empirical probabilities of events which were based on the results of actual experiments. So as you remember, basically whatever we did in class 9 was based on, for example, tossing a coin or throwing a dice or something like that. And these are called, and the probabilities that we calculated related to these events were called empirical or experimental probability. Meaning that the numbers that you have using which you calculate probability are actually based on experiment, or based on basically you could say that you could call that experimental or empirical data. So you have empirical data, and then using empirical data you calculate the same thing, empirical or experimental probability. So we discussed an experiment of tossing a coin 1,000 times, in which the frequencies of the outcomes were as follows. If you can remember, in the chapter that we just finished, we had the experiment using a coin, and we tossed the coin 1,000 times, and the number of heads and tails that we got was basically heads. We got 455 heads and 545 tails. So this was an experiment. And then based on this experiment, the empirical probability of a head, the empirical probability of a head was basically 455, meaning that the total number of times that the event happens divided by the total number of times that you do the experiment, which is 1,000 times, which is equal to 0.455. And the empirical probability of a tails would be, based on the same logic, 545 divided by 1000, which is nothing but 0.545. Now, basically, of course, you understand that these probabilities are based on the results of an actual experiment. So these two numbers are based on the results of an actual experiment. Of tossing a coin 1000 times. Now, for this reason, they are called experimental or empirical probabilities. So, empirical probabilities or experimental probabilities. So, and in fact, experimental probabilities are based on the results of actual experiments and adequate recordings of the happening of the event. Okay. Moreover, these probabilities are only estimates. So these one more thing that we notice about these such numbers is that these probabilities are merely estimates. What that means is that if you keep repeating this experiment a higher number of times, for example 2000 times, 3000 times, and so on and so forth, we will or we may get different results, because the numbers will change, of course. Now in class 9, we also tossed the coin many times and noted the number of times it turned up heads or tails. And we also noted that as the number of tosses of the coin increased, the experimental probability of getting a head came closer to basically the number half. So we tossed the coin for 4,000 times, and then we increased the number of times we tossed the coin. We increased this number, and then what happened was that basically this number, as you can see, this number is very close to 0.5, the 0 close to 0.5. This is the empirical probability of getting a head, and this is the empirical probability of getting tails. So as we increase this number of the times that we performed the experiment, these numbers got closer and closer to 0.5 or 1 by 2. And it says that not only you, but many other persons from different parts of the world have done this kind of experiment and recorded the number of heads that turned up. For example, the 18th century French naturalist Comte de Buffon, I don't know if I'm pronouncing the name right, tossed the coin 4,040 times and got 2,048 heads. So this French naturalist, I don't know what a naturalist is, but that must be something that you do. I don't know. The French naturalist Comte de Buffon, he tossed the coin. 4,040 times, 4040 times and got 2048 hits. Meaning that, well, half of basically 4040 would be 2020, and he got 2048 hits. The numbers are not very far apart, probably something about 10% or so. Not very far apart. So which is basically that would be a ratio of basically which would be a ratio of 0.507. And there was another gentleman from Britain, J.E. Carrick, from Britain, who did the same thing, the same experiment. He tossed the coin for basically 10,000 times, and he got 5,067 hits. 5,067 hits, which would be a ratio of 5,067 to 10,000, which would be 0.5067. That's the same thing as 0.51. Now there was another statistician, Carl Pearson. There was another statistician. Carl Pearson. Who spent more time, and he tossed the coin for basically 24,000 times. 24,000 times, and he got 12,012 hits. He got 12,012 hits. That's a ratio of basically 12,012 divided by 24,000, which is the same thing as divided by 2. You would get 6,006 divided by 12,000. Divided by 6, you will get 1,001, and divided by 6, you'll get 2,000. Divided by 2, you will get 5,000.5. I'm sorry, 500. This is 1,000. Divided by 2, you will get 500.5. Divide by 2, you'll get 1,000, and that would be basically 0.5005. Very, very close to 0.5. Now suppose we ask, so as you can see, as you increase the number of times that you actually toss the coin experimentally, or the number of times that you actually toss a coin, meaning that you actually do it, the numbers are getting closer and closer to 0.5, or basically the numbers are getting closer and closer to 0.5, or basically 1 by 2. And 2 over here is basically basically, if you can imagine that, for example, well, in the other chapter we said the total number of times that we perform the experiment, and over here you have I don't remember that definition. Okay, so basically we define that the empirical probability of an event E happening as the number of trials in which the event happened divided by the total number of trials. So the number of trials in which the event happened divided by the total number of trials. So what that means is that if I get basically 1 by 2 over here, that means that if I take the number of trials as 2, that would be the number of trials in which the event happens. And then of course you can multiply this number by any number, for example 10, 20, 30, 40, 50, and then you can say that based on that you can say that if you do the experiment for example 10,000 times, you're going to get, for example, 5,000 hits, and exactly half of that. So meaning that the numbers are basically getting closer and closer to 1/1/1/2. So now suppose we ask, what will the experimental probability of a head be if the experiment is carried on up to, say, 1 million times. So now let's try to answer this question. What will be the experimental probability? What will be the experimental probability of a head or heads if the experiment is carried on, if the experiment is carried on up to, for example, say 1 million times. 1 million times. Or basically, or you can say 10 million times. Or 10 million times, or even more than that. You would intuitively feel that as the number of tosses increases, the experimental probability of a head or tail seems to be settling down around the number 0.5, as we saw previously, which is what we call the theoretical probability of getting a head or getting a tail, as you will see in the next section. In this chapter, we provide an introduction to the theoretical, also called classical probability of an event, and discuss simple problems based on this concept. So basically, now to answer this question, what will be the experimental probability of a heads if the experiment is carried on up to say 1 million times or 10 million times or 100 million times or 1 billion times, and so on and so forth. And so since we saw that basically the numbers were tending towards 1/2 either for the heads or for the tails, we would say that basically no matter how many times we toss the coin, let's say for example 10 million times, we are going to get half of the time, exactly half of that time, heads or tails. So and that's basically that 1/2, you call it the theoretical probability. You call it the theoretical probability of getting ahead, of getting basically, for example, heads or tails. So basically the concept of theoretical probability, has also been called classical probability. Probability of an event. So what we are going to do in this chapter, of course, this is just a review. We are not going to do the exercises, but we will review basically. What we will review is that what we will basically we will first introduce theoretical, also called classical probability. We will do an introduction to classical or theoretical probability, and probability of an event, and then discuss simple problems based on this concept, and then discuss simple problems based on this concept. That's basically what we will do in this chapter. Now let's talk about theoretical probability. So let's consider this situation. So suppose a coin is tossed at random. Now I don't understand what is meant by random here, but let's go with the explanation. Let's see where it takes us. Suppose a coin is tossed at random. I don't know what that means. Let's see. And there is a part over here that says that when we speak of a coin, we assume it to be fair. That is, it is symmetrical, so that there is no reason for it to come down more often on one side than on the other. We call this property of the coin as being unbiased. By the phrase random toss, we mean that the coin is allowed to fall freely without any bias or interference. So first of all, there is two assumptions that we are going to have to make in order to be able to move forward. And that is two things. So I will talk about that. Okay, so now there are two things that we need to take into consideration here. So when we talk about the coin, what we mean is well, basically a coin that doesn't practically, of course, it doesn't exist in the world. It's a theoretical coin. It's a theoretical coin, meaning that we mean the coin to be a fair coin. We mean the coin to be fair, meaning that it is symmetric, meaning that the coin is symmetric, so there is no reason for it to come down more often on one side, so that there is no reason for it to come down more often on one side, than on the other. So that's the first thing that we need to take into consideration. and we call this property of the coin to be basically as being unbiased. That is an unbiased coin, meaning that the coin is completely symmetric. There is no reason for it to come down more often on one side than on the other, meaning that the coin is basically being unbiased. And basically the other point that we need to take into consideration is that when we say basically a random toss, what we mean is that we allow the coin to fall freely without any bias or interference. So of course that is not possible either. Practically that's not possible because there is always the interference of air and other forces in nature, but basically when we talk about a coin in theoretical probability, when we talk about the coin, first of all what we mean is that basically what we mean for the coin to be, we want the coin to be a fair coin, being an unbiased coin, meaning that it has no reason to come down more on one side than on the other side. And moreover, a random toss is that you don't interfere with how the coin is basically falling down. You basically allow the coin to fall down basically without any interference, without any bias, and meaning that the basically the process of the coin coming down is not being influenced in any way by you or by any other person performing the experiment. So we know in advance that the coin can only land in one of the two positions, in one of the two possible ways, either heads up or tails up. So we dismiss the possibility of its landing on its edge, which may be possible, for example, if it falls on sand, for example. And we can reasonably assume that each outcome, heads or tails, is as likely to occur as the other. We can reasonably assume that each outcome, basically heads or tails, is as likely to occur as the other. So we refer to this by saying that the outcomes, heads or tails, are equally likely. So that's basically, and these two sentences are important. We need to try to understand the meaning of them in different contexts, but again, I repeat them. We can reasonably assume that each outcome, heads or tails, is as likely to occur as the other. We refer to this by saying that the outcomes, heads or tails, heads and tails, are equally likely. So the outcomes, heads and tails are equally likely. Okay, so that is basically the situation. So for another example of equally likely outcomes, suppose we throw a dice once. For us, a dice will always mean a fair dice. What are the possible outcomes? They are 1, 2, 3, 4, 5, and 6. So each number has the same possibility of showing up. So the equally likely outcomes of throwing a dice are 1, 2, 3, 4, 5, and 6. So again, let's pay a little more attention to this. Suppose that you throw a dice once. Okay, so a dice, that is basically, that is what we mean by dice. We mean a fair dice, meaning that it's not biased towards falling or landing on any particular face, on any of its particular faces. It can, meaning that it has no reason to particularly fall on any of those particular faces. Meaning that falling basically on any face is now I cannot basically name a, since I'm saying that basically that the dice is not, it has no reason to basically land particularly on any of the particular faces. The only thing that I can logically say is that the possible outcomes, are basically 1, 2, 3, 4, 5, and 6. So each number has the same possibility of showing up. So the equally likely outcomes, so I can say that the equally likely outcomes of throwing a dice are basically 1, 2, 3, 4, 5, and 6. So of course you might basically you might come across many questions, many logical questions in your mind. I mean, this situation might not actually make complete logical sense to you, but that's the situation that we have to start with. Now, let's say that now the question is, are the outcomes of every experiment equally likely? Are the outcomes of every experiment equally likely? I don't know what is meant by this question. Are the outcomes of every experiment equally likely? Let's see what that means. So suppose that a bag contains 4 red balls and 1 blue ball, and you draw a ball without looking into the bag. So you have basically 4 red balls and 1 blue ball. You have 4 red balls. You have 4 red balls and 1 blue ball in a bag. These are all in a bag. And you don't look into the bag. You just draw one of those balls without ever looking into the bag, right? So what are the outcomes? So now over here, what are the outcomes? Now, to be more specific, are the outcomes a red ball and a blue ball, a red ball and a blue ball, equally likely? Now, since there are 4 red balls and only 1 blue ball, you would agree that you are more likely to get a red ball. You are more likely to get a red ball than a blue ball. So the outcomes, basically a red ball or a blue ball, are not equally likely, right? So that we can agree about. However, the outcome of drawing a ball of any color from the bag is equally likely. So I can say that the outcome of drawing a ball, of any color from the bag is equally likely. But of course you are always, in this situation, you're always more likely to get a red ball than to get a blue ball, because you have 4 red balls and you have 1 blue ball. So all experiments do not necessarily have equally likely outcomes. So that is basically what was meant by this question, which was not a very, I don't know why they asked this question, but anyway, so you can say that all experiments do not necessarily have equally likely outcomes. For example, in this and of course it's important to understand what is meant exactly by this question. see. Okay, so now what I think is meant by this, which is of course very important, it is very, very important, very fundamental thing in this chapter, is that we talked about some concept called equally likely outcomes. Equally likely outcomes. And what that means is that, for example, when you throw a dice, what happens is that you could get a 1 or a 2, a 3, a 4, a 5, or a 6. Now these are the 6 possible outcomes of throwing a dice. Now assuming that the dice is fair and unbiased, and also assuming that basically the dice the dice is thrown at random, so basically making these assumptions, then you can say that basically getting any number 1, 2, 3, 4, 5, or 6 as a result of throwing a dice, or let's say the dice, as a result of throwing the dice, which is basically the experiment that you're doing. So getting any number 1, 2, 3, 4, 5, or 6 as a result of throwing the dice you can call them equally likely outcomes. So these you can call equally likely outcomes. Now on the other hand, basically we had the example of the bag that contained, for example, 4 red balls and one blue ball. So basically in this experiment you pick some, basically you have to, without looking into the bag, you're drawing a ball from the bag, right? So in this experiment you are more likely to get a red ball than a blue ball. And so getting the outcome, or the outcomes of getting a red ball or a blue ball or a blue ball are not equally likely outcomes. You cannot call them equally likely outcomes. Now, for the sake of simplicity, because we want to be able to basically learn a couple of things about probability from now on, at least for the rest of this chapter, which is basically probability for related to class 10, we are assuming that every experiment has equally likely outcomes. So that's basically the assumption that we'll have to make in order so that we can basically move on. Now, in the previous chapter that we did, we did some sort of we defined something, and that was the experimental or empirical probability. That was the experimental or empirical probability or the empirical probability of, or let's call it basically P of E. P of E of an event E. And we define that as P of E was equal to the number of trials in which the event happened, number of trials in which the event happened, divided by the total number of trials, divided by the total number of trials. So now here it says that we have basically the empirical interpretation of probability can be applied to every event associated with an experiment which can be repeated a large number of times. The requirement of repeating an experiment has some limitations, as it may be very expensive or unfeasible in many situations. Of course, it worked well in coin tossing or throwing a dice, or basically dice throwing experiments. But how about repeating the experiment of launching a satellite in order to compute the empirical probability of its failure during launching, or the repetition of the phenomenon of an earthquake to compute the empirical probability of a multi-storied building getting destroyed in an earthquake. So what we have here is so it's not possible to repeat every experiment to get more and more number of trials in order to calculate the empirical probability of the event happening. For example, launching a satellite in order to compute the empirical probability of its failure during launching, that that costs a lot of money, and of course you cannot do that. So we need to have some sort of theoretical way of doing that, of course in such a way that the theory actually agrees with basically reality as well. So let me read this part again. It was the empirical interpretation of probability can be applied to every event associated with an experiment, which can be repeated a large number of times. So the empirical interpretation of probability can be applied to every event associated with an experiment, which can be repeated a large number of times. Now, the requirement of repeating an experiment has some limitations, as it may be very expensive or unfeasible in many situations. Of course, it worked well in coin tossing and dice throwing, basically experiments. But how about repeating the experiment of launching satellite in order to compute the empirical probability of its failure during launching? Or the repetition of the phenomenon of an earthquake to compute the empirical probability of a multi-storied building getting destroyed in an earthquake. So these are not the kind of things that you can repeat. So in experiments where we are prepared to make certain assumptions, the repetition of an experiment can be avoided. This is important. In experiments where we are prepared to make certain assumptions, the repetition of an experiment can be avoided, as the assumptions help in directly calculating the exact or theoretical probability. Now, the assumption of equally likely outcomes, which is valid in many experiments, as in the two examples above of a coin and a dice, is one such assumption that leads us to the following definition of probability of an event. Okay, so we said that in experiments where we are prepared to make assumptions. So this is important. So in experiments where we are prepared to make assumptions. That is assumptions. The repetition of an experiment can be avoided. The repetition of the experiment can be avoided as the assumptions help in directly calculating the exact probability. As the assumptions help to directly calculate the exact or theoretical probability and the assumptions, for example, the assumption of equally likely outcomes, which is valid in many experiments, as in the two examples above of the coin and of the dice, is one such assumption that leads us to the following definition of an event. So the theoretical probability, also called the classical probability of an event E, written as P of E, is defined as, so then based on these assumptions, you can say that the theoretical the theoretical probability also called the classical probability of an event E written as or denoted as P of E is defined as P of E. P of E is equal to the number of outcomes favorable to E, the number of outcomes favorable to E to this event, divided by the number of all possible outcomes of the experiment, divided by the number of all possible outcomes of the experiment. Of course, we will see what that means exactly. So P of E, or the classical probability or the theoretical probability of an event E denoted as P of E, is defined as the number of outcomes favorable to E divided by the number of all possible outcomes of the experiment, all the possible outcomes of the experiment. So now let's see what that means. And then there are a couple of assumptions that we make here, where we assume that the outcomes of the experiment are equally likely. Where we assume that the outcomes of the experiment are equally likely. So what that means is that meaning that you are basically considering some situation where, like, for example, where you're drawing a ball from the bag. So where you're drawing a ball from the bag, the outcomes of the experiment are going to be equally likely. Whereas if you, for example, if you have 4, for example, red balls and 1 blue ball in the bag, and then if you want to draw a ball, for example, at random from the bag, then what happens is that you're more likely to get blue balls, to draw blue balls, than draw basically red balls from the bag. And so the outcomes of the experiment are not equally likely, assuming that I assume that the outcomes of the experiment are, for example, drawing red balls versus drawing blue balls, right? So that's basically the definition here. So the theoretical probability or classical probability of an event E denoted as P of E is defined as this ratio, which is the number of outcomes favorable to E divided by the number of all possible outcomes divided by all possible outcomes of the experiment. So now let's see what that means. And now, from now on, at least in the rest of this chapter, we will refer to theoretical probability as probability. And this definition of probability was given by Pierre-Simon Laplace in 1795. Okay, and some history about Pierre-Simon or Simon Laplace. I hope I'm pronouncing the name right. So probability theory had its origin in the 16th century when an Italian physician and mathematician J. Cardan wrote the first book on the subject, the book on games of chance. So the Italian physician and mathematician J. Cardan wrote the first book on the subject of probability, and the book was called the Book on Games of Chance. Now, since its inception, the study of probability has attracted the attention of great mathematicians. For example, James Bernoulli, 1654 to 1705, or A.D. Moir, 1667, 1754, and Pierre-Simon Laplace are among those who made significant contributions to this field. Laplace's theory Analytique des probabilités 1812 is considered to be the greatest contribution by a single person to the theory of probability. In recent years, probability has been used extensively in many areas such as biology, economics, genetics, physics, and sociology, etc. So it seems that, and I want to check this again in case. Laplace. So it seems that Laplace was the greatest contributor to this field of mathematics, which is basically probability. And of course there has been some other people there as well, but it seems that the greatest contribution has been made by Laplace. Now in the next video we will talk about some examples here based on this definition of theoretical probability. So let's see what we have over there. I'll see you in the next video.